Thank you very much. I'm very grateful for the opportunity to take a holiday weekend in the U.S. and spend it here in Germany. For me, that's a very good deal. And I also feel a little uncomfortable is that I'm a pilot. I'm not a noise expert. So for me, this is going to church to confess my sins and to beg for forgiveness and do my penance. So I'll try to do that today. And the display I show up here now is a heads-up display that we used as part of a demonstration of RNP to GLS in San Francisco, California. And it just gives you a view inside the cockpit. We've got our altitude over here on the right, our speeds, and get a feel for the airport. Runway 28 right here is the primary approach that we were using, but runway 28 left is only 750 feet apart from centerline to centerline. When we talk about GBAS, there are three key components. The first being the Global Navigation Satellite System. Several countries have them in operation or soon to be operational. GLONASS, Galileo, and GPS. The second component is located at a specific airport. Frankfurt is one of the global leaders in this regard and have a system that's been operational for quite some time. And lastly, you have to have aircraft that are equipped with a GLS system. GLS is the type of approach we fly using the GBAS system. And our Airbus aircraft, it's an optional system for the newer Airbuses, plus the A320 can be turned on for operators of those aircraft. With the newer Boeing aircraft, it's a standard or baseline product, so there's perhaps better equipage there. And on the 737 next generation aircraft, which is what I fly, Delta chose to buy the GBAS or GLS option, and I'll tell you a little bit about some of the things we've learned. The operation of the system, you take the airborne, or the GNSS element is transmitting to 4 very precisely located receiver antennas at an airport. And those antennas compare, they know exactly where they are. They compare where GPS thinks they are. They send that information to a terminal for processing, which then develops a very precise location update, which is transmitted by VHF data link to the airborne aircraft. If the aircraft is properly equipped, it can receive that signal starting right out here. It comes through our localizer and VOR antenna, along with information from regular GPS antenna, our navigation control panel, where we have to tune a channel for the specific approach that we're flying with the GBAS. And we also use what's become more older-fashioned inertial reference unit inputs to this multi-mode receiver. And once that information is synthesized in the multi-mode receiver, it can be sent to our flight control computer, which operates our control surfaces of the aircraft. If we are using the auto flight system, the autopilot, we get our display units, get the information, so we can interpret the data as pilots, along with a heads-up display if the aircraft is so equipped. And then our flight management computer system is also taking advantage of that information. This allows us to fly an
Deswegen können wir RNP to GLS im Anflugverfahren nutzen. Und Sie sehen hier die verschiedenen GPS-Informationen, die direkt von den Satelliten gesendet werden. Und dann werden sie in diesen grünen Bereich beim Landeanflug übertragen. Und hier sprechen wir dann
section of the approach. What you see in red is a more traditional vectors to a runway approach and landing, and it's just a conceptual, allowing you to put the concept together in your mind and see what we can do. As far as benefits, as an airline, very much like Condor, we have to manage our finances and we look for a return on investment. At Delta, right now, by the end of this year, we will have approximately 100 aircraft equipped with GLS capability. At the end of next year, about 150, and just under 200 the following year. So what are the benefits of GBAS and GLS? In many ways, they are in the eye of the beholder. We can eliminate the ILS hold short lines, which is good for the airport, it's good for air traffic and the operators because we can have less taxi time to the runway and get airborne. As a pilot, I very much like the fact that unlike the traditional ILS system, it does not have what we call a false glide slope that will bring you down to the ground prematurely, or a mirror glide slope that may have you climb prematurely, adding power to do that climb also if the auto flight system's on. The traditional ILS has what we call a bending localizer. At times, the signal can be bent and cause an uncomfortable ride for passengers or a unsafe situation to develop if it's not caught soon enough. Typically, there are safeguards in place to reduce the chance of a bending localizer in instrument conditions, but if we use the same system in visual conditions, it can cause us problems. The GBAS has a little bit longer range or service volume than the standard ILS, and we have found in the United States last winter, we had Winter Storm Jonas, and in the New York area, the Port Authority operates 18 ILS systems, and they have one GLS or GBAS system rather at Newark Airport. Well, during the course of the storm, all 18 ILSs went out of service at some time due to snow removal and snow accumulations blocking the antennas. The GBAS system, it kept on working fine, and the United Airlines aircraft that were equipped with GBAS kept coming, as did Lufthansa, who made several flights during that period and were able to get in while other airlines had to cancel operations or divert. The TCAS is something that affects us in the approach environment at times and reduces the chances of collisions with other aircraft, and it's more specific to the airport we're looking at. And lastly, we also want to reduce fuel burn, we want to reduce carbon emissions, and most important here today, we want to reduce noise. But we also looked, well, let me talk about introducing GLS. Perhaps Europe is a bit ahead of the United States in this regard. We have two airports, Newark, New Jersey, and Houston, Texas, that have operational GBAS units. There are a couple of others, but they are not public sites. They're operated by Boeing for some of their evaluation purposes. And initially, we anticipate GBAS will be used to overlay the same flight paths and vertical paths as the ILS approaches that exist today. The second phase, we see an increase in the glide slope angle, and I'll talk about 3.25 degrees that we used in our demonstration in San Francisco. And the reason for that was Boeing was our manufacturing partner, and all the Boeing aircraft are certified to 3.25 degrees for the Autoland system. Airbus may be the same, I don't know. I'm trying to find the answer to that. And our phase 3 is more some of the advanced concepts that we were trying to demonstrate with GBAS, and that's what our San Francisco demonstration was all about. As far as San Francisco as an airport, it has some challenges. Number one, noise, as does every airport. It also has some terrain issues. There are a couple of runways where you really can't efficiently, you can't do instrument approaches to two of them because of the terrain is so close, and a couple more, it limits the minimums to which you can fly your approaches. There are airspace constraints with airports very close by in Oakland, San Jose, and NASA's Moffett Field. And weather is frequently a factor. By San Francisco Bay, we get fog and low-level clouds on a regular basis. And then the runways itself are a challenge because they're two parallel sets of runways intersecting each other at 90 degrees. So it was a good airport for our demonstration, plus both Delta and United Airlines had GLS-equipped airplanes that we could go fly at night when they were not in revenue service and test these advanced concepts. So what did we do? We've got up here on this diagram, hopefully you can read it well, but number one is to runway 10 left, and the 3.25 degree glide slope allowed us to have a precision approach where none exists today. What that means for us as pilots and the operation is that the current RNAV approach is limited to 1,200 feet. If we don't see the runway by that point, we must execute a go-around, which creates a lot more noise than continuing to land. And with the GBAS GLS approach, we were able to get down to about 300-foot minimum. So certainly an operational benefit. The one that I'm going to talk about most a little later in the presentation is number two, which was a constant descent approach to runway 19 right, which today has no precision approach capability. And then we did a couple of approaches over here on number three to runway 28 right. And I'll discuss those, but runway 4, each time one of the airplanes flew the approach to runway 28 right, we had a second airplane from either Delta or United flying the approach in sequence to 28 left. And on that approach to 28 left, we used the existing ILS system, and that has a 2.75 degree glide slope and has for many years, as long as I've been flying into San Francisco. And that created a vertical difference between the aircraft, which allowed for some reduced separation. From a pilot's view, this is what we work off in the cockpit. And this is the approach to 28 right. It's what we call GLS Whiskey to runway 28 right. And as you can see, it leads in this longer portion leading to the final approach. We designed it to fly over San Francisco Bay instead of over the populated areas. And then we didn't initially intercept the GLS final approach course until we got in closer. At about 2.9 miles, we made that transition to the actual final course guidance. And another view of this, and I'll try to keep my pace moving along here, is in blue, that's just the standard ILS approach to 28 left, and then the GLS Whiskey approach that we developed. And basically, we're trying to allow pilots to get into a position where we're clear of clouds. With the existing approach today, that has to be done by 1,600 feet above the ground, where the pilot has to be clear of the clouds, see the traffic to the left runway, call it in sight, and then complete the maneuver using the RMP to GLS for the final approach segment. This is just another depiction of that same approach, showing that we kept a lateral separation of at least 3,000 feet until we had the visual sighting of the other aircraft, and then we maneuvered to the left and to the right at relatively close range to intercept this approach guidance, which, if you notice, has a displaced threshold of about 2,000 feet. I couldn't resist to show you my office the night we did the demonstration, but basically these lights would be two red and two white if we were on the glide path for the traditional approach at the regular threshold, versus we were now aiming for a threshold up here where the airport authority was kind enough to put some construction lights, and we had a visual cue to back up what was programmed in our navigation database and ensure that we were in fact flying a good path. This is the GLS Victor for runway 26 right, and maybe this is an easier slide to look at. Our goal here was twofold. The first being to reduce the vertical or the horizontal separation between the two pairs of aircraft going to the respective runways. Today, it has to be 1.5 nautical miles between the two aircraft as they come in. And we felt with the procedure we developed, we could get that as low as 0.6 nautical miles, which would compress the noise, I guess, during a period and allow greater windows for arrivals or departures on the intersecting runways. The other goal was today, the aircraft to the left runway must always be 757 or smaller. So that's a sorting challenge for air traffic controllers to ensure that they have the right aircraft going to the runways that are capable of handling the approach and still respecting the wake turbulence separation criteria. So this is really what noise people want to talk about. And this is our report that came out on the 18th of November. I have not briefed my boss on it yet, so I'm telling you what I think about these things at this point, and we're more than willing to share the final report with you. If you're interested, please let me know. Realize that this was not just Delta Airlines. This was San Francisco International Airport was kind enough to host our project. The FAA controllers in the tower and the TRACON worked with us in developing this, and some of the folks from the Tech Center came out and flew with us during the approaches. United and Delta each provided an aircraft and crew and were involved in development of the approaches. And Boeing was kind of the mother. They helped organize this all and kept us pointed in the right direction. And Jeppesen provided our navigation databases and the approach charts that we needed as pilots to fly them. All right, so let's talk noise. Runway 19 right. It was, for me, the most interesting approach to fly, and I think we were pretty successful, but the preparation leading up to the flying involved optimizing the ground path, and to do that, we looked at 260 aircraft flight paths, and we reduced those to a long vector route in blue and a short vector route in red. And overlaying here in green is what we designed with the GLS, the RNP to GLS approach. And interestingly enough, I'm going to show you a slide later on about the noise reduction, but the short vector route actually was not as good from a noise perspective reduction than the longer route, and it will make more sense here in a moment with a future slide. So once we had the ground track with the idea of reducing noise exposure, we had to think about optimizing the vertical flight path coming down. And we found what worked well for this particular demonstration was 300 feet per nautical mile, and above 3,000 feet in our target software system that we used to develop the approach, we used 3+ nautical miles above 3,000, and it got a little tighter below that because we were slowing as we flew the approach. Another nice benefit of this approach is Oakland Airport is right here, and that's runway 12. And today, you cannot simultaneously land on runway 12 at Oakland and the 19s at San Francisco. If this approach gets implemented, both airports will be able to operate, and we've procedurally separated the approaches with vertical separation. So how did we fly it? We really worked hard on the design. We had the good lateral path and a good vertical profile. And we went out to fly. I did something a little bit different than what we did in the simulators at Boeing in anticipation, and we got a little bit better result. We were obviously trying to minimize the use of speed brakes and delay our configuring of the aircraft to keep the throttles in idle as long as possible. And it's hard to see on this approach plate, but we started at Westla, which is almost abeam the runway at 6,000 feet above the runway. And when we did that, we used flaps 2 and 180 knots, and the throttles were in idle. And the throttles stayed in idle during the descent until we approached Cody 2. While the throttle stayed in idle, but we added flaps 5 to start slowing down, and we never leveled off. We kept the descent coming completely, contrary to how it's depicted here on the approach. We kept a constant descent, and then when we reached 2,000 feet above the field elevation is when we dropped the gears, went to gear, and then flaps 15, and continued slowing and configuring the airplane. We were very pleased with the results. And this is based on the modeling we did as opposed to the actual flight results. But the big message on here is with the ground track and the vertical path selection, we went on the long vector route, affecting 296 plus thousand people with decibel levels above 55. 329,000 or more were affected with the shorter vector. Even though it's shorter, it went over a more densely populated area of Oakland. And then we only affected 47,300 people flying the GLS Victor to runway 19 right. And you can see how it was quiet, and that's about where we went to flaps 5, and then later on where we started adding more flaps, and eventually the landing gear and the power coming up for the landing. This is just another depiction of those three approaches. And basically at the bottom you have distance in nautical miles and altitudes. And you can see when we started the long vector route in blue and the short in red, we're at 6,000 feet, 210 knots typically in flaps 1. But these went much further out, 40.3 miles for the long route and 36.3 for the short route. And you can see they did this step down to 4,000 feet where they added flaps, they added power and noise, and then we started only at 20.5 nautical miles from the runway for our ground track, and we flew at the 3.25 degree glide slope, which we did for every one of these approaches, the 3.25, versus the 3 degree that exists with the GLS to, well, there is no ILS approach to 19 right. It's just a RNAV approach where they were flying that glide path. And in summary, up here you can see based on the long vector, short vector, and GLS, and is that too small to read? Okay, the big message here is we reduced the mileage by 19.8 nautical miles from the long. We saved 556 pounds of fuel, 1,754 pounds of carbon emission, and you can see on this slide below, we reduced from it by about 250,000, 280,000 people being affected above 55 decibels, down to the 47,300 number I showed you earlier. So we were quite pleased with the results, and actually the GLS here, we did better than the modeling forecast and the simulators. They had us flying at 424 pounds using during the full 20.5 mile track, and we actually flew 327 pounds, so almost 100 pounds better. Just summarizing things here, we've got, where do we go from here? We were very happy as an airline with the results of this demonstration, and not just Delta, but the whole team. We felt we took some things from the theoretical to the practical level, and we're hoping that we'll be able to implement some of these things at San Francisco and other airports. But we have the terminology in German was a little bit different, but in English, it's which comes first, the chicken or the egg. And there are airports that are looking at this system and installing it, and we very much wish to work with our airport partners to see the installation of GBAS units so we can start taking advantage of some of these benefits. The manufacturers of the aircraft and the airlines have to step up and make the investment in equipping the aircraft. Air traffic management, people need to build constant descent angle approaches and initiate approaches at higher altitudes. In Europe, I think you're better at keeping your flight paths and altitudes higher as long as possible, and I think that's an area we need to work on improving in the United States. And we need the cooperation and the support of the air traffic controllers and the pilots. And with regard to some of these challenges, it's interesting, today at Delta Airlines, we have our OPSPEC authorization to fly Cat 1 GLS approaches with our 737s and our A321s, but with only 2 airports in the U.S. that operate it. I am reluctant to do the training and have the pilots prepare to fly, and then it may be several years before they actually get to fly a GLS approach. So we're hoping we can get that chicken in place so we can start producing eggs and get pilots out flying the GLS. Thanks so much.